about why like we're at kind of a like obviously we moved super quick in this class, but I think it would be cool to just mention like why we're at a really cool place now. So previously in the lab, like for instance, the kind of stereotypical example for electrostatics, which means charges are not moving, they're kind of at a particular place, is our lab one, where we had like a charge. We manufactured two charges on the plane, and then we studied the electric field around them. Similarly, for magnetostatics, that's kind of when the charge is steady throughout a thing. So for instance, when we kind of set up our magnetic force thing, we had a steady current going through and observing the behavior. So steady currents is magnetostatics, and not moving charges is electrostatics. Now we're on to kind of a joining of both of these two ideas. So we're onto something called electromagnetism or electrodynamics. There are two names for the same thing. And so the thing that describes this theory of electromagnetism are four equations called Maxwell equations. You probably don't need to know them at this point, but I think one of the cool things about this, now that we're onto this phase where charges are moving and currents are changing, is because this theory of electromagnetism, Maxwell's theory, was what led Einstein to derive his special relativity. If you look at, let me get these meeting controls out of the way. If you look at what Einstein's paper was on special relativity, his kind of relationship between space and time, the title of it was actually had nothing to do with special relativity. It was called On the Dynamics of Moving Bodies, or on the Electrodynamics of Moving Bodies. So it's a very weird kind of, I guess a lot of the t-shirts, slogans with electromagnetism is it has a lot to do with the blending of space and time, as well as the speed of light. One thing you notice here, and don't worry about the form of this equation, but that's the speed of light there, c, the speed of light. And so if you were to describe these equations with kind of like verbally, if you were to just say what they mean, it means that when charges start to move, so like instead of in lab one where we just had the charges sticking to the sticking to the plane, as soon as the charges start to move, they actually create magnetic fields. Similarly, instead of steady state currents, if we allow the currents to change over time, that creates electric fields. So that's kind of explains why there's this duality between electromagnetic fields with time and magnetic fields in space, and this relationship that Einstein used to derive special relativity and go on to general relativity. In particular, let's just focus on one of these equations. This is when you see this triangle here, that's like a spatial derivative. So this is a curl. So if I were to write out, what does a curl look like, it would be the derivative over all the spatial components. That's not a curl. Just curly hair. So it's kind of like, where are we going here? Here, so you see how like when you write out a curl, you're taking derivatives over each of the spatial components. So in English, you can kind of describe the curl as the spatial derivative of the E field. And on the right-hand side, we have a time derivative of the B field. So that kind of gets at this changing in space goes to changing in time. This is not, this derivation right here is not super important. I'll just go through it really quickly. If I were to integrate both of these things over an area, some kind of square or something, and so I integrate over an area, and I have this area element on each side here. One kind of fundamental theorem that you use a lot in when you get to kind of electromagnetism and all these integral and differential calculus terms is called Stokes Theorem. And the way it works is that if you integrate something over an area, that is equivalent to integrating over a length element around, so this little circle on the integral means that I'm integrating around the outside of the figure. So instead of integrating this area in the center, I'm integrating the length around the outside. And that's called Stokes Theorem. So if I do that on this left-hand side, the same thing on the right, or actually not the same thing on the right-hand side. On the right-hand side, what I'm using is the fact that when you do things in calculus, either take a derivative or integrate something, it doesn't matter which order you do things in. So instead of integrating the time derivative, I can take the time derivative of the integral. And so now that I have this integral here, this looks just like that equation that I used with Gauss's law when we did the two parallel plates, and I mentioned I made that Gaussian pillbox or Gaussian surface, and I counted the number of E lines going through it, which was equal to the flux. This is the same thing, but in a magnetic field sense. So this integral of B over an area is called the flux. It's the number of B field lines that go through an area. And so now I'm going to define, so this is the time derivative of the flux on the right-hand side. And on the left-hand side, this integral of the field over the length of that square or surface I'm using, I'm going to define that as something called the EMF, or the electromotive force. It's a very crappy name because this, the units of this thing are not a force, they are a potential. So just like we did in electrostatics, this symbol, this curly E that you see in textbooks a lot, you can also call it a V, and that's what we'll do in the lab manual. So this is kind of the form that we'll use in the lab manual, and I'll get to why we use that right now. So this form here is kind of, it's defining this thing called inductance, and it's extremely similar to capacitance. Remember that when we were defining capacitance, it was really, like theoretically, it was really just something that allowed us to relate one formulation of an answer for the electric field to another formulation of the answer for the electric field. Inductance is kind of a similar thing. I'll explain it like this. If I take, oh, of course I'm not the right page. 1 second. This is a pretty good book on electromagnetism, and I'm not at the right page. Here it is. Okay, so one of the consequences of this, changing magnetic field creates an electric field is kind of that when you take one surface, so for instance, let's talk about this current loop here. Imagine like our Helmholtz coil, except only one of them had current going through it. When the current goes through this, it creates the magnetic field. Remember, we know that when things go around the coil, that it creates a magnetic field in a particular direction. So we've got this particular direction of the B just kind of arbitrarily going through things. And then we have a second loop. So imagine this loop has no current going through it. However, now it has a B field going through it. And so what happens is it's very similar to kind of the Newton's law, where if force one acts, or if a force from one object acts on another object, the opposite force is kind of equal and opposite to balance it out, so that the sum of the forces equals 0. This is a very similar effect where the magnetic field of loop 2 will be created to balance loop 2, because there's no current going through loop 2. So why would there be a magnetic field? And so what ends up happening is there is a kind of induced current going around loop 2 in the opposite direction as the first eye. Oh, I'm sorry, in the same direction as the eye. And you could also kind of relate this to our circling electron from the last lab. So with this, we can also calculate what the magnetic flux on 2 is due to 1. And we call this something called the inductance. You can ignore this kind of M. We'll replace it with L in just a second. And the way we get from here to that equation is if we take the derivative of both sides. If we take the derivative of the flux and we take the derivative of this side, this M is just a constant that tells me because the B of this field depends on the current, It's just, I know at most that the magnetic field felt over here depends on the current of I. So this is just, again, it's very much like that capacitance that we did from before. So this inductance is kind of this constant that allows me to define how much of is felt over here, and it doesn't change. So if I take the time derivative of this side, the only thing I'm taking the time derivative of is I. So it kind of passes right through the L. And when I say L, that's called, more technically self-inductance. And the reason that forms is because you can assume, this is kind of the stereotypical picture of what we're using today. It's called a solenoid. And you can kind of approximate it as pretty much like this picture where there are two rings and they influence each other. Just because they're, these things are connected in the solenoid, if you look at your system that you have on your desk, it pretty much looks like just a bunch of circles linked up together. And so this self-inductance is exactly the same thing as the inductance that we were looking at before. But when you see this, we know that the magnetic field is shooting through the center of this. So in the center, we know the magnetic field is going this way. But what actually ends up happening with each of the kind of like, if you think of these each as little circles, on the outside, they kind of create their own little magnetic fields. And so that's what this inductance is. Here's a little better figure of it, where you see inside the magnetic field is shooting to the right, and the induced EMF is kind of acting with it. Let's see, where have I gone? Here it is. So if I take the time derivative of both these sides of the equation, if I take the one on the right, I end up with what I have over here, right, without the minus sign. If I take the derivative of what I have on the left-hand side, that's exactly this Faraday's law that we had from before. The time derivative of the flux is equal to this EMF, or as they call it in the lab manual, which is a V. And the derivation of this comes kind of from the geometry. So you can think about the geometry of the particular solenoid and to determine what that constant L is that kind of relates the two formulations of the magnetic field. And now in particular, I'll point to what I found really helpful this week was actually what Rich mentions in usually these little, right here. So this chapter 30 of Giancoli is phenomenal. I usually don't refer back to that actual book because I think this Griffith's book or Purcell electromagnetism books work better, but this one was very good. Like all the derivations that you need for the background are there. So at the moment, I'm just going to kind of show the screenshots of all the pages from there. I think it lines up with chapter 30. I downloaded an international edition, but this corresponds to chapter 30 of the actual book. So this is kind of, we know that when inside the solenoid, it is proportional to the number of turns and the current going through the solenoid, where this number of turns is kind of a number of turns per unit length. And that unit length is helpful because we can use, instead of Gauss's law with that like box that we had with the electromagnetic field, we can draw circles called Amperian loops and use Ampere's law, which tells us that it's very similar to Gauss's law, just in a slightly different form. It's that the line integral of B is equal to the current enclosed. So that you can compare this to the area of EA, I believe it was epsilon, and the charge enclosed. So they're practically identical equations, but we use them for each electric and magnetic field. And so that's what we get from this equation here. And rearranging that, we can find the following, which matches exactly with what we have in the lab manual. Now, once we get to actual circuits, I find the lab manual to be pretty hard to understand. However, again, this chapter 30 of the book derives it pretty much exactly. And so I thought this was very helpful because in particular, like a lot of the discussion questions rely on these differential equations. And I think differential equations are incredibly hard and kind of not altogether useful all the time. I think understanding where they come from is a bit more useful. So I just wanted to, in a similar way that I did last week, kind of like flash, so when people are going back to this video, they can, pause the video and look at this derivation. It basically follows from what you'll use in the actual discussion question, because most of these are incredibly hard this week, is just this one. It's called deriving equations. You derive 3, which corresponds to this equation in the textbook, just from Kirchhoff's law. So you have, voltage of the battery, voltage drop, and you explain why those are voltage drops. But this derivation here is the simplest that I've found of this, and I really like it. So I just wanted to pause there. If people want to come back and understand why this time constant, kind of the decay of the voltage in the circuit, which I'll get to on the board as soon as I finish up here. Similarly, once we get to LC circuits, actually this is still LR. So one feature of the LR circuits is, this is what you're going to see in lab today, this kind of exponential decay of your voltages. However, here, what they're doing is plotting your current, which is accurate. The current is decaying also, but what you can also do is the voltage, because we know that the voltage is proportional to how the I changes. You can also look at this. So this equation right here is synonymous to that I equation here, because if the current changes, the voltage changes. And so that's where they get that equation. What they're doing here is they're taking the natural log of both of these, and they do that for the following reason. Let's quickly just say, just to review really quickly, when you take the natural log of e to the exponential, what you end up with is just the thing in the exponent. Where is it? Right here. So if you take the natural log of an exponent, both of those things kind of cancel, and you're just left with the argument up in the exponent, x. So that's what they're doing here. And the reason they do that is because v, in particular, I'll get to it on the board, this is something you can measure, as well as time. So now we can compare this to y equals mx plus b. You can just ignore this plus b. It ends up not having any effect. It's just kind of the v that you put into the equation, which in this case just comes from the outlet that we're using. So here we can compare this to y equals mx. So we have this, our objective is to find the inductance. And if we use that equation from the textbook, that tau, this time constant, is the inductance over the resistance. We're going to set the resistance, find tau, and solve for L. So that's how the first part of the lab works. The second part, this differential equation is even more difficult. Thankfully, this chapter in Giancoli is incredible, and it has the exact derivation. So again, you can find the exact equation, the initial differential equation that you want to solve from Kirchhoff's rule. So just that the sum of circuit elements around a circuit sum to 0, the potential drops. Again, to me, this is not a familiar differential equation. So I just wanted to pause on things like this to give you an idea of how these derivations work, because for me, honestly, up until now, these are non-trivial. I understand them now, but it took me quite some time. So what you're doing in this part of the experiment is you're kind of getting, and let's see if they actually, LC. This is, if you recall, when I asked that question when we first did the oscilloscope, why a this kind of circuit setup is similar to the harmonic oscillator. We'll see it even more here. Why can't I see it? Oh, it's an LRC. We're not. Oops. Anyway, what you'll see on your oscilloscope this time, which we were struggling to see the first time, is this. So now we have a resistance, a capacitor, and an inductor, and it is exactly like a driven harmonic oscillator. So what we're going to do in this part of the lab is we're going to find the period by counting wavelengths, similar to how we did earlier in the lab. And then we're going to use those wavelengths to get the period, and we're going to compare each of these equations. You can just ignore this little zero I wrote on the board. That you really don't need the zero. And then you can set these two equations equal to each other, something found experimentally, something set experimentally, the capacitance, you'll set it yourself. And then again, you solve for L. And in both cases, they should agree, and you should, match it up with this equation. So this is the theoretical equation, and your job throughout the lab is to match it using these two experimentally found L's. Okay, so now I'll get to kind of the practical tips. I think that's all I had here. Just some cell phone pics. What else was over here? Nothing. Okay, so I'll stop recording now. As usual, I don't have the meeting controls up, so I can't see. Okay. If anyone has any questions, if not, I'll get right to explaining the kind of practical tips on the board. Okay, as usual, I'll post this with the discussion question reminder. Again, it's just that Kirchhoff's law one, but I'll post it in the announcements. Okay.